This is a brief introduction of the paper, Deep Clustering by Semantic Contrastive Learning. In this paper, we work on a task called deep semantic clustering. As a long-standing unsupervised learning technique, clustering has been widely studied for a few decades to partition a set of imagery samples according to their prefixed feature representations. Recently, along with the rapid development of deep learning models, clustering has been exploited together with visual representation learning to separate a set of raw images into the desired number of groups without pre-learned features. However, considering the complex visual patterns and their arbitrary combinations existing in natural images, a set of unlabeled images can be separated in multiple different ways according to different criteria. Whilst not all of the separations are meaningful, it is critical to learn semantically plausible clusters so that the feature representations and cluster memberships of samples can be used to facilitate further analysis. To that end, we investigate the task of deep clustering in terms of the consistency between the learned clusters and the manually defined semantic classes. In this case, each learned cluster can be described by a human understandable word or short phrase like the class labels. In the past few years, contrastive learning has been shown as a powerful self-supervised learning technique which can yield instance-wise discriminative feature representation of images without requiring any human annotations. It is also attracting growing attention for its potential benefits to explicitly inferring class decision boundaries in deep clustering. To that end, except for the conventional sample-specific contrastive learning which learns with every sample as an independent pseudo-class, there are also attempts to jointly explore samples' uniqueness and local neighborhood structure or additional clustering objectives. Directly applying sample-specific contrastive learning to deep clustering is suboptimal for class discrimination. This is inherent in learning with per-sample pseudo-classes generated by global linear data augmentations. Although exploring local neighborhood structures is able to learn from realistic intra-class image variations, the size of neighborhoods is usually restricted for maintaining their class consistency. Besides, the simple combination of instance contrastive learning and clustering objectives is prone to contradictory learning supervision because the former aims at pulling away samples within clusters while the latter pushes closer. However, such a contradiction is overlooked by existing attempts on benefiting deep clustering by contrastive learning. In this paper, we propose a novel variant of instance contrastive learning to learn class discriminative feature representations of images and their semantically plausible partitioning without using any manual labels. The proposed variant is called semantic contrastive learning. The key ideas are to resolve the inherent contradictory learning objective of contrastive learning to class discrimination. By doing so, we are able to learn the decision boundaries of clusters according to the visual similarities between images encoded in their feature distances. Our semantic contrast is a generic formulation. It can be utilized by any instance contrastive learning methods for deep clustering tasks. The below figures compare the framework of MoCo and RSCL. The main refinement is to add the component of contrastive sets at the cluster level in a plug-in manner. With such a design, the SCL model is end-to-end trainable, therefore globally optimized for both representation learning and clustering. In conventional instance contrastive learning, the contrastive set of samples is constructed randomly. Even though meaningful visual features can still be obtained when instances are identified against arbitrary samples regardless of their inherent class memberships. Thanks to the contrastive learning formulation, the SCL model is robust to the randomly initial and the unreliable intermediate cluster assignments to be trained from scratch with random feature representations and decision boundaries. With each sample being assigned with a pseudo-label, the SCL conducts instance discrimination across clusters to pull instances away from only their pseudo-negative samples of other clusters in a representational space. After that, the decision boundary of clusters will then be updated to assign samples into the cluster with the closest anchors. By iteratively updating the model weights and samples pseudo-label, the SCL finally leads to cluster discriminative imagery features and semantically plausible cluster assignments. To conduct contrastive learning without being contradictory to clustering, we introduce a semantic memory to construct per-sample contrastive set at the cluster level and finally enable cross-cluster instance discrimination. The semantic memory is composed of C-independent feature queues as the memory banks for C clusters with a one-to-one mapping between them. The SCL then constructs the contrastive set for each instance by the feature stored in all the memory banks except for the one corresponding to its own cluster. And the loss function for instance discrimination is to identify each sample by its augmented counterparts from its contrastive set. At the beginning of training a randomly initial model, the contrastive sets are composed of arbitrary samples. Hence, our SCL degrade to conventional instance contrastive learning. With the visually similar samples being gradually assigned into the same clusters, the learning objective of representation becomes reducing visual redundancies across clusters. At the end of the training, the learned feature representations are supposed to be cluster discriminative rather than at instance level. Besides, considering that each memory bank in the semantic memory is storing a set of samples from a cluster, they can naturally serve as the anchors to describe that cluster. In this case, given the feature of an image, the SCL computes the distances between it and the anchors of every cluster to measure the likelihood it is from different clusters. Such a distance-based cluster structure is then used to supervise the decision boundaries by cross-entropy loss. By doing so, different clusters will gradually absorb visually similar samples and exhibit consistent and unique visual characteristics. To further enhance the discrimination ability of SCL, we discover the hard samples which are confusing to the model as frequently being assigned into different clusters at different training epochs. We emphasize those hard samples in discriminative feature learning by increasing their weights in a batch so to encourage models' awareness of their specificity. With all these designs, the overall training objective of SCL is the weighted sum of instance and cluster discrimination losses. Both the pseudo-labels and weights of samples are updated per epoch. We evaluated the SCL method on a wide range of deep clustering benchmark datasets. Whilst it yielded competitive performances in most cases, its advantages are much clearer in finer-grained and larger datasets like ImageNetDogs and TinyImageNet. Moreover, we also observed the significant performance margins obtained by all contrastive learning-based methods. This indicates compellingly the benefit of contrastive constraints and unsupervised semantic concept learning. We also investigated the effects of different components in SCL. From the ablation studies, the independent contributions of both cross-cluster instance discrimination and online cluster discrimination are notable. Moreover, their benefits are amplified when being used together. This demonstrates the mutual benefits of representation learning and decision boundaries reasoning. In the visual cases study, we visualized the correctness and confidence of samples cluster assignments and observed the high consistency between the two metrics. This implies the semantic plausibility of the learned clusters to be consistent with the manually defined classes. More detailed evaluations and ablation studies can be found in our paper. We are happy to discuss if there are any questions. That's all. Thanks for your attention.